All right, so now we're going to go over practice problems 2 and 3 for stormwater. This is where we're actually analyzing the affordable house that we've designed. So before we even get started, a few assumptions I'm going to make is that everyone's calculation should actually be different for this, depending on the house that you designed and the driveway and if you put a patio or any kind of sidewalk in. All right, so what I'm going to do is for my house, area for the house is going to be 1,200 square feet. Area for the just do parking lot or driveway. Let's just say D, and that's going to include the patio and sidewalk and anything like that. I'll just say it's 1,000 square feet. All right. So when we do our analysis for post development, those are the things that are going to be different for everyone. So make sure that you use your values. But this is just a video for how to go about this. All right. So some information that we're going to be using. We're going to be using Noblesville, Indiana, the 100-year 1-hour design storm. So when you go here, I already got it pulled up. So there's the closest station to Noblesville. The 100-year 1-hour storm is 3.05 inches per hour. So I here is going to be 3.05. 3.0. Did I? Yeah, 3.05. Yes. Okay. So we know that undo that. I is equal to 3.05 inches per hour. That's for this. Assume the existing site is flat with clay soils, unimproved runoff coefficient of 0.2. So we've kind of actually been given C 0.2 there. We can just kind of go back to the sheet here. Oops, what just happened? Let's undo whatever I did there. All right. Yeah, right there. So let's see. They're just saying to use a poor drainage clay soil 0.2 just to make our life easy. Okay, so that's what we're going to do. So C is 0.2. And we're going to do two different analyses for the post-development. There's going to be an option 1 and option 2. I'll go over that as soon as I'm done with the pre-development. So pre-development, we're going to have, so if you actually go through the to AutoCAD and take a look, or not AutoCAD, Revit and take a look at the site, the area of the site, and I should have done that, area of the site is 1/2 acre. All right, that's the overall area of the site, approximately. So area is 0.5 acres. We've already said, is 3.05 inches per hour. C, they told us, is 0.2, and CF for a 100-year storm is 1.25. So for pre-development, Q pre is, whoops, what just happened? Is CF CIA, so it's 1.25 times 0.2 times 3.05 times 0.5. All right, so you do that multiplication. 1.25 times 0.2 times 3.05 times 0.5, and you get approximately 0.38 cubic feet per second. All right, so that's our pre-development number. All right, so now we need to go through our options. All right, and this is going to take a bit of space, so option 2 is going to be on a different page. Option 1, there's no stormwater management system, so the roof is asphalt shingles, driveway is just concrete, and the whole site is just turf grass, no landscaping. All right. So turf grass, no landscaping. So we have 3 spaces: area for the house, area for the driveway, and area for landscaping. So we know this is 1,200 square feet divided by 43,560. The area of the house is 43,560 is approximately 0.03 acres. The driveway, 1,000 divided by 43,560 is 43,560 is approximately 0.02 acres. And so we have a half an acre minus 0.03 minus 0.02. So we have 0.45 acres remaining. So the C for the house, so worst case scenario for asphalt shingle or shingle roof is 0.95. For concrete, pretty sure I saw the same thing. Concrete, 0.95. That's the worst case scenario. C is 0.95. And for the lawn, so let's see. Poor drainage, up to 2% slope. But yeah, the site's really flat. So we're going to use 0.17. All right, so C is equal to 0.17 for the lawn. So to figure out our composite C value, we have C sub C is 0.03 times 0.95. Let me zoom in here. Plus 0.02 times 0.95 plus 0.45 times 0.17. All that still divided by the total area of a half an acre. And we should get approximately, so let's just type this in, 0.03 times 0.95 plus 0.02 times 0.95 plus 0.45 times 0.17, close parentheses, divided by 0.5. You should get approximately 0.25. All right. And so the option 1 Q value, let's do that over here where we have a little bit of space. Q is equal to 1.25 times 0.25 times 3.05 times a half an acre. So 1.25 times 0.25 times 3.05 times 0.5. And we've increased our runoff to 0.48, rounded up, cubic feet per second. All right, so it was 0.38, now it's 0.48, so a tenth of a cubic foot per second increase. And now we need to look at option 2. So we'll do this later. So option 2, see page 3 for option 2. Okay, so we're going to go all the way down to page 3 here. I've got a blank page down here. So option 2. All right, so option 2, if we went through there, let's go back up here and just show you. So option 2, it's trying to take as much, it's a low impact affordable house design. So the rainwater from the roof is all captured in barrels or a cistern. Therefore, there's no runoff from the roof. You've trapped it all. You're going to maybe use it for gardening or irrigation of some system. The driveway and sidewalk are constructed from permeable pavers, so you can get a lot more water going into the soil. And then half of the leftover lawn area is being planted with native plant material instead of this turf. All right, so we have the area for the house. We have the area for the driveway, we have area for half the lawn, and we have area for the other half of the lawn. All right, so we can kind of copy and paste some of our values here. So we know that the area of the house was, if I remember correctly, is 0.03 acres. This is 0.02 acres. And it was 0.45 left over. So 0.45 divided by 2 is 0.225 acres. That means this other one is also 0.225 acres. The runoff coefficient here for the house, it's 0. Remember, all that stuff is being trapped. All right. So for the driveway and all that stuff, for permeable pavers, let's see. So permeable pavers are assumption. Let's see. Permeable pavers. Where are we seeing this? City residential. Asphalt, concrete, shingle. All right. So best I can say is we're using the lowest case values. So lowest case that I'm seeing for any kind of driveway or other surface like that, maybe like your brick area. So the whole point is to use the lowest case here. So maybe 0.7. And then half the lawn is being planted with native soil, materials. All right. So there we would use something a little bit lower. So we would use the lowest case value. See where the 0.13. So that's the best case scenario. So C is equal to 0.13, and then the other case, C is equal to 0.17, which is the same as before. All right, so our new composite C value is 0.03 times 0 plus 0.02 times 0.7 plus 0.225 times 0.13 plus 0.225 times 0.17. Again, all that still divided by our half an acre. So our new composite, don't need to worry about the 0.3. So it's point open parentheses 0.02 times 0.7 plus 0.225 times 0.13 plus 0.225 times 0.17. Close parentheses, divide that by 0.5, and you should get approximately 0.16 cubic feet per second. So we have actually reduced our runoff using option 2. So before our runoff was 0.38, and we have less runoff after development. So that's a good thing. We don't need to do anything else. We don't need to do a drainage or a detention system or anything like that. We have less runoff, so we are all good. All right. So what size water storage tank? So question 3, what size water storage tank would you recommend in order to collect the volume of water that would fall during the 24-hour, 2-year, 24-hour storm on the affordable house? How would you install sufficient water storage? All right. So we have two different first of all, so the 2-year, 24-hour storm system. So we go back here. So the 2-year, 24-hour is 2.83 inches per hour. All right, so the 2-year, 24-hour storm is, if I'm getting this right, the 2-year, 24-hour storm is 2.83 inches per hour. Somehow my notes that I'm looking at have something different, and I want to make sure that I'm saying the right thing right now. Yep. So 2-year, 24-hour, 2.83 inches per, for the whole thing. So that's what we're going to use. 2-year, 24-hour, 2.83. 2-year, 24-hour storm is equal to 2.83 inches. All right. So that's our I value. Or that's the really not the I. That's the amount of water that we're looking for. So we're looking for so 2.83 inches falling over our entire half an acre. All right. So you need to calculate the volume of water for 2.83 inches over 1/2 acre. So there's this unit that engineers use. It's called acre feet. So you're figuring out how many feet of water are spread out over this entire area. So the concept is, if just to draw a quick sketch, if this represents 1 acre, and then the depth, so right here, it's the depth measured in feet of water. So that's how it turns into a volume. If you see that picture there, it's kind of like a cube right there, or some kind of rectangular prism. All right, so we know we have a half an acre, and we have 2.83 inches, but we need to convert that to feet, so divide by 12. And so we have 0.5 times 2.83 divided by 12. Oops. 0.5 times 2.83 divided by 12 is 0.118 acre feet of water, which doesn't really make a whole lot of sense. So to really get an understanding of what size or quantity of water, we need to multiply by the number of acres, or convert from acres to actually feet. So multiply this by 43,560 square feet per acre. 43,560, and you need to take care of a total volume of water of 5,136 cubic feet of water. All right, so we need something that will accommodate this amount of water. So just pick something that's kind of like I wouldn't call it totally a random number, but a depth of a trench, or a depth of a pond that is you would feel safe. So maybe a couple feet deep, maybe 3 or 4, 5 feet deep. So if we take 5,136 feet cubed divided by 5, I'll just kind of pick a random number. So now I know my trench, or my swale, needs to now cover a surface area of 1,027 feet squared. So if I just quickly kind of take the square root of that number, take the square root of 1027, you get approximately 32 feet. So the idea is, if you dug a trench or a drainage detention pond that's 5 feet deep, it would need to be 32 feet by 32 feet to hold all of the water on site temporarily until it can slowly either drain into the soil or drain off site safely. You can obviously make these any dimensions you want. You can make it a shallower number. So if you don't want to use 5 feet, you can make this number shallower, but then these numbers here have to be bigger. It can be rectangular, it doesn't need to be square. But the whole point is you need to somehow match or make up this volume of water that's going to be landing on your site for this storm. And that's the process that most engineers go